So we this morning, for those who didn't join us, we talked about digital twin and Industry 4.0, and then in the second module we talked about an introduction to simulation to get us all on the same page, and then an introduction to Simio. In the third module, we talked a little bit more about Simio, and we went through a simple model and talked about experimentation and analysis, and a little bit about randomness and distributions. So now in this section, module 4, we're going to talk a little bit more about Simio library highlights, talking specifically about source object and sync object in a simple model. Then we'll talk about constant whip problem, just as a simple example to illustrate. We'll spend a fair amount of time talking about this server object because not only is the server pretty important, but it also illustrates a lot of what's available in the other objects as well. We will then quickly touch on batching and separating, and a quick overview of material handling with conveyors, and then vehicles and workers. So that's going to be a pretty full hour coming up. So let's get going on it. All right. So to start with, the Simio library, it only has 13 objects. But the objects are pretty dense. They have a lot of capability in them, and that capability is addressed under properties. And more specifically, they're groups of properties. And so what we have tried to do to make it more understandable and easy to use is that we have categories in each one of our objects, and those categories tend to have a lot in common, and in some cases they are identical from one object to another. So for example, once you learn what's in the buffer logic of one object, you'll know what's in the buffer logic and how to use it of every other object. Some of those are, as an example, the buffer logic that we've already touched on a little bit in the last object, last module, was looking at input buffer and output buffers and how the capacity by default is infinite. But that you can also have limited capacity, and if you have limited capacity, you can also choose bulking and reneging options, which are basically when I first arrive at the queue, maybe I decide not to stay, that's bulking, or after I've been there for a while, you might decide to leave, and that is reneging. So all of that is built in under the buffer logic category of all the different objects. State assignments we'll talk about shortly, but states we talked about earlier very briefly, but states are things that can change during a run, as opposed to properties cannot change during a run. And the states, this is a typical interface for states, is that there are a set of places where you can assign a state. So in this case, in the server, we have when you first enter the server, you can change a state. Just before processing, you can change a state. Just after processing, you can change a state. And these states could be the state of an entity that is being acted on, like a part, or a resource, or a fixture, or the server itself, or the model itself. So for example, if you just wanted to count the number of parts through something, well, in most cases, things are already supplied for you, and that one is one of those. But if you wanted to add that, you could add the state assignment here. An interface that we haven't seen yet that will be coming up is called a repeat group interface, that whenever you see this ... here, it means that you have the option to do more than one thing. So you can choose just to assign a state like increment a counter or something, or you can do multiple different states. Financials is another example that Simio provides complete activity-based costing. including capital costs, waiting costs, that's the buffer costs, resource costs, costs while idle, costs while per use, or costs while being used, and capital costs as well. And then those costs can be rolled up to any specified cost center, and those cost centers can be rolled up to other cost centers. So you can get complete costing reports across your model, and that costing can be in any combination of the world's currencies that you would like to have. So you can specify that a cost is incurred in pesos and summarized in yen, should you like to do that. Okay, so the source is the first object we're going to talk about in detail, and we've seen it just a little bit in our earlier models, but we'll see it a little bit more here. Dynamic entities are what enters at the source. So this is typically the parts, the people, the customers that flow through your system. When they come in to the source, they wait at the output buffer, which in our last module, we set that as 1. So they wait at the output buffer until they can move into the output node and then move on to the network. There is a lot of automatic capabilities built into Simio to, for example, block something from leaving the source if it has no place to go. So there's a lot of capabilities already built into that. Some of the properties of the source include the entity type. So what entity am I going to create? And there are provisions to link this together with data tables to allow you to say 10% of the entities I produce are, let's say, low severity patients and 20% are high severity patients, or whatever the domain might be. We also have arrival modes, which I'll go over next. Entities per arrival, buffer logic, the bulking that I just mentioned, stopping conditions to say, when do I stop creating entities? In the source arrival mode, we have several different arrival modes for specifically. We have the inter-arrival time, which is what we already used in the default arrival mode that just says, my first entity comes in at this time, at time offset, and then every subsequent entity takes a sample from a random exponential distribution with a mean of 0.25 and creates an entity every interval after that. That, of course, does not have to be random. It does not have to be exponential. You could say, I want to create an entity every 3.5 minutes, and it'll create an entity 3.5 minutes. The pluses, wherever you see times, or just in general, wherever you see the pluses, it allows you to put units in. So in this case, if you hit the plus, it would give you a choice of seconds, minutes, hours, days, etc. In many cases, particularly customer service applications, your inner arrivals don't come in consistently throughout the day. So if we think something like a coffee shop or a call center, you might have entities coming in at, let's say, 5 minutes apart, in the morning, in the early morning, and then maybe 20 minutes apart in mid-morning, and then 7.5 minutes apart, during lunch break, etc. And so this uses a special construct called a rate table, which is a tabular information that just specifies how my rate varies over the course of the period. Typically a day, but not necessarily a day. And you can specify any period length you want and any sub-period length. So I could have, the most common would be 12 1-hour or 24 1-hour periods to an hourly arrival over the course of a day. But you could just as easily have 10, 17-minute periods if that fits your application better. One nice thing about this is once you get that arrival rate all set up, there's something called a rate scale factor in here that allows you to change that by any amount that you like without messing up the distribution itself. So you can say, well, what if I had a 10% increase in my arrival rates, but following the same relative arrival rate schedule? You can do that easily here. And like we did in the last one, we experimented quickly with using control variables. You can make this a control variable so that you could experiment with multiple scenarios. Say, well, what's my base case? What is it with a 5% scale factor increase, a 10%, a 20%, a 30%? Okay, another type of thing is an event. So you can have event-based arrivals. Now, events require a little bit more explanation. What is an event? Well, an event is the way that is one way that different objects, independent objects, might communicate with each other. And I like to illustrate this with my favorite event being my birthday. So on my birthday, I might broadcast an event saying, hey world, it's my birthday. And all of the intelligent objects in the world would be watching for Dave's birthday and immediately go out and buy an expensive present for me. However, if you're my family, where my birthday, I've had enough of them now that it's pretty much a non-event. And so if you're a part of my family, then you would ignore it. Unless, of course, you're my oldest daughter, who is, let's say, thrifty is a common word for it. Cheap is another one, but we'll go with thrifty. On my birthday, I can count on it. The very first call of the day I get will be my oldest daughter on my birthday will say, happy birthday, Dad. Where are you taking me and the family for dinner tonight to celebrate? So I can always count on one response to my event. So anyway, events are a very efficient thing. They're essentially free in Simio because they only take overhead when they're used and triggered. And so there are lots and lots of automatic events included in Simio. And so that would be an easy way, for example, and we'll see this in just a moment, in a conwhip system. One way of implementing a conwhip system is to say, I only want to create a new entity when another entity leaves a certain part of the model. And so this is looking at leaving an entity. When an entity leaves or enters this input node at the sink, it triggers an event, and then that event is picked up by the source and creates a new entity at that point. So every time an entity leaves, an entity comes in. And finally, another type of arrival is arrival table. And this, at its simplest level, is just a spreadsheet, a table full of arrival times. And so you can just specify, I have arrivals at time 1.5, 3, 3.25, 4, 8, 25, whatever it may be. And so you'll get arrivals entering discretely at those times. So by default, it is discrete arrival times. However, there's also a field called arrival time distribution. And so if you put something in here like random uniform -10, +10, then that means every arrival will come in within plus or minus 10 minutes of its scheduled time. So there are other fields in here that you can use to randomize the arrivals. But this is a very powerful thing, particularly when it does not have to be just a single column in that table, but you can put as much characteristics of the entity being created as you wanted. So you could have 10 characteristics. It's due date, it's resources required, any types of information that you wanted about it, part family, could be put in that arrival table. Okay, on the flip side, so that was how you get entities in. This is how you stop creating entities, and there are three primary ways. Either you can do it with a maximum arrivals, as in count. So this is saying after I have 25 arrivals to this source, I will stop creating arrivals. And or you could do a maximum time to say after 8 hours of producing, let's say I open the bank door for 8 hours. After 8 hours, I close the door. Now, this doesn't mean that I stop processing the entities in the bank. All it means is that I close the door and don't let any new, entities come into the bank. And then the last one, again, just like the event that was my birthday, you can have a stopping event that says, hey, stop creating any new entities at this source when something in particular happens. And then I mentioned earlier the assignments, just a couple more slide builds to give you an idea of what that does. So I indicated that this little ellipse or dot, dot, dot here keys that there is a repeatable group there. When you first load that, you get a somewhat scary looking interface that basically says on the left side is all of the current members of the repeat group. So is there, okay. Can you hear me okay? Hello?
Yes, we can.
Okay,
yes.
Right. A message came up about audio.
Oh,
okay. So on the left side is showing all the current members of the repeat group, which we have none, so that blank thing looks kind of scary. On the right side is the current repeat group. So until you put something in it, it looks kind of questionable, but as soon as I add something to it, I hit the add button. In this case, I've hit the add button twice, and I've added 2 items to the repeat group. And then the right side of that repeat group looks a whole lot like the properties window because it is a properties window for this one item in the repeat group. So what this is telling me is that I want to take the priority of the model entity. Remember, if we read these from right to left, it's often easier. So the priority of the model entity, I want to assign it to a value of 12.5. And then the picture of the model entity, I want to increment by 1. So I want, if it came in as a 3, I want to go out as a 4. And this is something you might often do if you have a series of pictures, maybe representing a part buildup or an entity changing. You can just increment it and go through that set of pictures very easily with assignments. Okay, and then the last object I want to talk about here is the sync, and this will be a really quick conversation. The sync basically has 2 jobs. It records a time and system for every entity that passes through it, and then it destroys the entity. So that's pretty simple. So let's build a simple model. So I'm going to create a source and a sink. Shouldn't take us very long. Connected by a time path, and we'll experiment with that a little bit. Okay, so those of you that are modeling along with me, again, if you don't have a clean slate, I recommend you do a file new to get us back to a clean slate. So now that we have this, we want to bring in a source at one side. And by the way, if you have a scroll button on your mouse, you can use the scroll button to scroll in and out. So I'm going to scroll out a little bit, make this a little bit wider, and put a sink in here. And then I'm going to connect it by a time path. So I'm just going to single click on the time path, go from the source to the sink. And at this point, I'm just going to leave everything constant, or leave everything at its default. So the travel time on the sink is 1. And we don't have to do this, but just for completeness, I'll bring in a default entity. And let's run the model. And there's our entities coming in at random times. So the entities are arriving at random exponential 0.25 minutes apart. And then they each take 1 minute to get from the source to the sink. When they arrive at the sink, they get disposed. Okay, if we wanted to make this run a little bit faster, we can go to the Run ribbon. And we looked at this just before. There's two ways to control the speed. Well, we can do a fast forward, which turns off the animation and just goes fast forward. Or we can adjust it doing small adjustments here by changing this faster or slower. Or for big adjustments, we can go up here and change this to, for example, 10. And now you'll see it running much faster. Okay, let's move on to a ConWhip workshop. So normally these are workshops that I would have you do, but we'll do it together for time and expediency. So we're going to use the source. Well, I guess we'll create a new model called source server sync, spaced about 10 meters apart and connected by time paths. We're going to use all default properties, except we're going to change it so that we have a constant WIP, which is what ConWhip stands for, constant work in process of exactly 4 entities in between the points where the red arrows are. Okay, so let's do a file new. By the way, there are ways we could have just changed the model, but for simplicity, we'll just do a file new. And we want to place a source, a server, and a sink. And we'll connect these by time paths. So I'm going to this time double click on time paths and do my first time path from source to server 1 and my second time path from server 1 to sink. So if we just run the model now without doing anything else, there's my first entities coming in, and let's set this maybe at a 5 to make it go a little bit faster. And again, this is with all default properties. So the default properties say we come in basically 0.25 minutes apart. At the server, it uses a triangular distribution with a minimum of 0.1, a mode of 0.2, and an average of 0.3. And then they go to the sink, and our 2 time paths take 1 minute each to get from one place to the other. Okay, so that's the basic model. Now, what would we do for a ConWhip? For a ConWhip system, we can change our inter-arrival time to an on event. So when we change it from on event, then we have some new properties that come up here, including how many entities do we want to have to start with, and what is our triggering event that causes them to stop. So again, if we look back to the model, what is our triggering event that says create a new entity? Well, our triggering event would be whenever it leaves the server, we want to create another entity because we want to keep 4 within this zone here. So our triggering event here, if we look at it, there's our different choices in this little model. You can see all the automatic events that are already in there. And we might want to say output at server 1. So whenever we leave server 1, and whether we enter or exit the output is relatively, doesn't make much difference. But let's say every time we exit the output at server 1. So that is, this is the output at server 1. Whenever we leave that on the path, then we're going to create a new entity. Now, if we did this now, can anybody guess what we would get? We would get a model that is not too interesting because no entities are created. It's running. You can see it's running down here, but nothing is happening because no entities were created. We said every time an entity gets here, it'll create one. But until something gets there, we won't create one. And until we create one, nothing will get there. So in order to make this work, we have to have some other stream of entities coming in here to kick it off. And one easy way to do that is number of entities here. So we can specify initial number of entities here as 4, and then we'll have 4 entities come in. And let's see what happens with that. Oops, did I not do that right? I thought I typed 4 there. Okay, so we have 4 entities come in. Now there's our 4 entities, and no matter how long an entity takes to process here, we will still have 4 entities in the system. So that's our simple conwip system. And we could experiment with other things like our different options here: in arrival time, time-varying arrival rate, on event, arrival table. All of those will bring up different properties to control how it works. Okay, let's go on now and talk a little bit more about server. As I said, the server is kind of our workhorse. This is the one that does, you'll use in pretty much every model. And the server itself, we've seen kind of indirectly by looking at the green lines. It has an input buffer where entities can wait for service. It has a processing buffer where entities wait while being processed, and it is an output buffer while they're waiting to get on the network on the way out. But the server has lots more capabilities, including the ability to automatically follow a work schedule. So you can say you work from 9 to 3 with a 45-minute break at 11. And so you can follow that, and if it follows that, then you'll see outside of those times, it won't be processing anybody, but it could process during those times. You could also say the server is always available, but it requires a secondary resource, a person, in order to operate it, and that person follows the schedule. So either of those would effectively result in the same thing. It can rank and select from the entities that are waiting. It has reliability, failures and repair time. So let's go through some of these. So the default capability in server is that everything is what's known as statically ranked, as in when an entity enters the queue, it stays at that place in the queue. It won't automatically shift around, particularly if you use one of the rules like first in, first out, or last in, first out. However, you can also rank it based on smallest value first of any, or largest value first of any expression you want, and a common expression to use is entity priority. So that way, if a priority 3 comes in and waits at the beginning of the queue, and a priority 1 comes in after that, it would move in front of the priority 3. If a priority 2 came in, it would move between the priority 1 and the priority 3. So you can do that, and in this case, in all cases, the resource will automatically always pick whatever's first in the queue whenever it goes idle. So that is static ranking. Then the opposite choice of that is dynamic selection. So note the different words: static ranking, which ranks how things are in the queue, or dynamic selection says, I'm not going to always select just the first member of the queue. I'm going to apply a rule to determine which one I should select. And you can see that there are a lot of built-in rules that are actually fairly sophisticated rules. Smallest and largest priority, those are pretty simplest. Earliest due date, that's pretty simple too. Least setup time and critical ratio, those are much more comprehensive rules. These would be used, least setup time is what's called a local optimization rule that basically says, if I'm now, taking the diagram here, if I'm now producing a red and I choose least setup time, then the next one I might choose might be the red because there's no setup time to go from a red to a red. Maybe from a red to a purple is only a low amount of setup time. So after I use this red, then I might choose this purple and then this purple. The least setup time does what's best for this server. Now, critical ratio is what's known as a global optimization rule. And it's somewhat complex if you're not already familiar with it, but critical ratio is the ratio of total processing time remaining to the total due date or time until due date remaining. And so it will look at all of the projected processing time for that entity going through its sequence of production steps and compare that to its due date. And something that has only 1 day left would probably be prioritized ahead of something that had 5 days left. So again, those are just illustrative. There's lots of rules in here, campaigning rules, things like that. And you have multiple tiebreakers, et cetera. So this is where part of the power of the scheduling engine comes from, is that you can put really sophisticated logic in here, having an unlimited number of rules. We've got some models that have 8 or 10 different rules like this. First you apply least setup time, and then you apply critical ratio, and then if there's a tie, you use the least slack time, et cetera. And all of those rules, if you want, could be custom-made rules done in the API through BASIC or C# or something like that. Although most people find that the rules we have don't require that. These rules can be, as I mentioned, local or global optimization, or even a user selection rule. The server itself can go on and off shift, and as it goes off shift, you have a choice. Do you want to suspend the processing or finish the work that's already started? You can also, if neither one of those basic options applies, then we have add-on process triggers. Oops. Then we have add-on process triggers. And we briefly talked about processes, I think, in the second module. But processes are places where you can, well, a process is a set of logic that can do anything you want. An add-on process trigger is a place in the sequence of actions of that module where you can put any of that logic. So this indicates that whenever an entity goes off shift, I want to execute a process. And in that process, you might say, okay, well, figure out how important this entity is. If this entity is not important, then just let it wait until the server comes back on shift. If it is important, then maybe look around for another server that could do this entity and transfer that entity over there. Or if there is no other server, then keep this worker on shift until that high priority part is processed. So you can do any arbitrary logic like that you might want to do. For secondary resources, you have those same things, plus you have an extra rule called switch resources if possible, which addresses the situation. Let's say I have a set of operators, Bill, Frank, and Mary, that are on different shifts, and I seize Bill for during the first shift, and then Bill goes home, what do I do? Well, this can say, well, look and see if Frank or Mary are available, and if so, switch directly to Frank or Mary. Okay, another aspect of server is reliability. So we have 4 different types of reliability, which basically represents failures. And so we can say that it fails, based on a calendar time. So this one fails on average every 40 hours, or it fails based on processing count. It fails, on average after every 27 parts, or it can be processing time, which would be more like tool wear. So if my tool typically fails after 6 hours, then I would put an expression resulting in an average of 6 hours under processing time. And then you can also do event counts, which that's the catch-all for anything. You can create any custom event at any time. And so an event might be a power failure in plant A. And so whenever there's a power failure in plant A, this particular resource would fail. For all of those, you can specify time or count between the failures. And again, you can customize with processes to say when it fails, go do something. When it's repaired, go do something else. Secondary resources, it's probably just easiest at this point to shift over and go into the software and show you what this looks like. This is a little bit more on financials, expanded out, how you can specify any currency in the world and specify costs or reporting in any currency you would like to have, and rolling up as desired to any set of departments. Okay, so let's build our simple little model again, or maybe we already have it. And let's look at the server itself and look at some of these things. So I mentioned that it could follow a schedule. So you can say follow a work schedule. And there is a work schedule built in called standard week, but you can have any type of schedule that you would want to have. This just happens to be an 8-hour-a-day, 5-day-a-week schedule. If you specify fixed, that doesn't mean it can never change. It just means it doesn't automatically change. You can change the capacity of resource at any time. So for example, I used to joke about US Airways, and I guess I can talk about them now because they don't exist anymore, but US Airways, I thought they had such abysmal customer service that they would always reduce the number of servers on a line to make sure that everybody had to wait at least 45 minutes. So they might have 5 people on. If the line gets too short, then they take one person, so they go on break. So you can do that easily through Simio. This is where you'd specify the ranking rules, first in, first out, or smallest or largest value first. This is where you'd specify the dispatching rules, where you can specify any type of dispatching rules and any number of them that you wanted to have. Our processing time, like we've seen before, is specified here. It does not have to be random. And although we haven't discussed it yet, I guess I don't have a good place to talk about it today. So I'll mention that you could read this time from a table. I talked in the first module about data-driven models, which basically says, like for a server or for a part, I might have a data table, a spreadsheet, that lists all the characteristics of that server or how it responds to different parts. And so I could tell this just to go to that data table and figure out what processing time you need to do based on what you're now processing. So that's a pretty powerful feature. Buffer logic we talked about before, same as we saw in the well, we saw this in the server. We also saw it in the source object, where you can specify different capacities as well as bulking and reneging options. Our reliability, so there's our 4 different types of reliabilities: calendar time, event count, processing count, or processing time based. State assignments, we looked at state assignments in the source. You can see that state assignments in the server look identical, with the exception that we have lots more trigger points. So we can change it at any 4 of these basic points, plus whenever an entity bulks or an entity reneges, we also can assign things at that point. Before I show you secondary resources, I guess I ought to put a secondary resources in. So let's say we have a couple of workers, and I'll come back to this later and show you. I have 2 workers there, and I want to add those workers to a list called, operators. So now I can go into my server, into my secondary resource, and say that I need a resource. Yeah, let me make this false. I need a specific resource, and the worker and the resource I need is worker 1. And so that's going to say I need worker 1 to be available before I can process at that server. I can also choose to bring that worker to my location or to any specified location. So I can say, well, bring it to input at server 1. And it doesn't have to be there. It could be anywhere. And so now this is going to say, whenever I want that worker over there, I want him, whenever I use him, I want to move him over there. So I'm looking ahead a little bit here, but let me, while I'm at it, I will add a node in here and call this my worker home. So there's my worker home node. And for my 2 workers, I want to tell them that they start off at worker home. At worker home. And whenever they go idle, I want them to go back to home again. Okay, so now I've got worker 1 and worker 2, worker home, and I want them to come to this node whenever they're busy. So let's see what happens. So now the worker's gone over there, came back. So he goes back and forth as he becomes idle and busy. Now I could also say here, instead of choosing a specific worker, since I put them in a group, I could say, well, select from a list of workers, and the list of workers is the list called operators. So now it would choose either worker 1 or worker 2 to do that. That's choosing worker 1 all the time because he only chooses 1. But if I set the capacity of this to 2, saying that server has 2 workstations in it, now both workers go over and both workers are busy. And yes, you can stop them from looking like they're standing in the same place if you wanted. Okay, so what else? Financials. Yeah, I think we've covered most of that. All right. And by the way, I only just now realized, because we started our lunch at an odd time. Do I have an hour? Oh, I guess I still have an hour. 2 o'clock. Yeah. Okay. Okay, another concept is batching. So batching is basically where you want to, the typical use is that you bring things together for processing all together as one, and then split them apart again. So for example, a box of parts or a tray of parts or a pallet full of boxes, anything like that would be considered a batch. And so a batch is done by a group of member entities can be batched and carried by a parent entity. So we look at that as, in the examples I gave, the member would be the part, the parent might be the tray of parts, or the pallet of boxes or something like that. And so you can put as many members as you want to be carried by a single parent. And generally speaking, you're only processing that parent. So if you go through a process step with a pallet of 20 parts, typically your processing time is per pallet, not per part. But you can split up that pallet at any time. You can drop off parts at any location. And you can even do hierarchical batching. So for example, you could create a batch of parts, 20 parts into a box, 30 boxes onto a pallet, 5 pallets into a truck, send them someplace by truck, and then at the first stop, drop off 1 pallet, send that pallet someplace where it might drop off 3 boxes, split open those boxes to get the 20 parts in each box. So you can batch and split at will. The batching is taken place by the combiner, which if you cover up this member input buffer and member input, it looks and behaves almost exactly like a server. So it is a server with 2 different ways of entry. So it has all of those same things, the reliability, the processing time, the costing, financials, all of that is everything that the server has, combiner has as well, but it also has the ability to combine members and parents together. And that can be a simple like 1-to-1 or 1-to-5, or you can combine any number of things. So you can say, in order to make this pallet, I need 1 red part, 3 yellow parts, 2 green parts, and 1 blue part. And so it will wait until it gets exactly that combination of 7 parts. And when it gets that 7 parts, then a pallet will come out. And there, I mentioned earlier SymBits. So there are a number of SymBits available to illustrate, how combiner works. So a regenerating combiner basically it represents something where it recycles the pallets. So you never run out of pallets. Multiple entity types on a pallet is basically what's illustrated here. Releasing a batch early is something like, let's say I want batches of 10 and I produce 100 parts, but 2 of them fail somewhere along the way. So I only get 98 parts that come to the combiner. What do? Well, I would create 9 batches of 10, and then using this release batch early, I could make another batch of only the 8 rather than waiting forever for 2 parts that are never going to come. So there's a lot of flexibility in with combiner. Now, as you might expect on the opposite side of combiner, the matching object to that is the separator. And so a separator, again, looks identical to a server, behaves identical to the server, except it has a member output buffer and some extra capabilities to deal with that. The main function of it is to separate a batch of entities. So I have a box with 20 parts in it. I come in here, the box goes out the parent output, and the 20 parts come out the member output. But it doesn't have to be a complete split. So I could put 2 parts come out the member, and the parent and the other 18 parts go out the parent output. You can also use this to clone from the parent or even create another entity type entirely. So one entity could come in here. Let's say a passenger at an airport comes in with a state saying, I have 3 pieces of luggage. And this might represent the ticket counter. At that point, maybe the passenger comes out this way, and we create 3 entities representing its 3 pieces of luggage that come out this way and hop on a conveyor for the luggage conveyor. So you can use separator to not only separate batches, but also create new entities. Let me show you a quick example of the typical way that this has worked. I think that maybe it might sink in a little bit better. So I'm basically just going to create parents and members. Let me start with a file new again. Okay, so I'm going to create two sources. So I double clicked on the source to get two sources. I'm going to zoom out a little bit with my scroll button. By the way, I guess I never mentioned up at the beginning, if you're still seeing this, these are tips to give you all of those different buttons. And the one thing you need to memorize off this is the H key, which is what I just pressed, hides and shows that. But if you ever wonder, how do I zoom in? How do I do anything? Hit the H key and read through that list, and it'll probably tell you what you need to know. Okay, so I'm going to do a source. I'm going to do a combiner. I'm going to do a server. Let's scroll out a little bit more. I'm going to do a separator. And then I'm going to put in two sinks. And I don't necessarily have to do this. I think the flow will happen automatically, but I'm going to put in paths. I'm going to double click on the paths and connect all these up with paths. Okay, so I've done nothing else here. Let me put in a couple of entities just so we can distinguish between the entities. And I haven't showed you this yet. So if I wanted to make this entity red, for example, I can go up to, I clicked on the entity, click on the color, click on red, and then come back down here. And I just zoomed in so I could click on the entity. So I just made that entity a red entity. I could do the same with this, or I could change its size. But instead of either one of those, I'm going to apply a symbol to it. So I said I wanted this to represent a palette. So let's make it represent a palette. We can go into my animation, my drawing view, place symbol. And there's a number of different ways you can place symbols. You can choose symbols from our library, or you can import a symbol, a file that you have on your system, or you can go to 3D Warehouse, where there are literally millions of symbols available. But I'm going to go in here and just select a palette. Oops, but I think let me do that again. Click on the default entity. I think I clicked off of that somewhere along the way. So I'm going to click on the palette there. So that replaced the entity with a default entity. Replaced the default picture with the picture of a palette. And then I guess while I'm here, I can say, well, I want the entities to appear on the palette. So I just went up to the draw queue batch members, and I'm just going to draw some, just a big line there like that. And that will be where the entities sit on the palette. Okay, so if we just run this now, well, no, I didn't quite do it right because I forgot to tell source 2 that I wanted to create the model entity 1. And by the way, rather than these names, we might just call this palette. So I just clicked and clicked again on the entity. So click again, and make this part. So part and palette. Note that those are not simply names, but those are actually associated with it. So now source 1 is creating a palette, and source 2 is creating a part. And I'm combining a part and a palette together. So you can now see one part on each palette. Now that was using all the defaults. If I wanted to instead say that there are 3 parts on a palette, then I just told the combiner 3 parts on a palette. It waits till there's 3 built up. And so that's my combiner. And then over on the other side of this, we see the next time one comes through. There it is. So they come to the separator, pallet goes one way, or the parent goes one way, the members go the other way. Okay, so that is combiner. And I've been doing an awful lot of talking, so let's see, where are we at now against our deadline? So I guess I have another 5 minutes, so I'll if you can hold your questions for another 5 minutes, let me get through my other 20 slides. Not happening, but okay. So another type of material handling we have is conveyors. So Simio can model pretty much any type of conveyor you have: bottling conveyors, luggage conveyors, roller conveyors, cleats, bin conveyors, bulk continuous handling, and my personal favorite, power and free conveyors, where you have a structure that is carried around, that carries parts around, and that moves. It hangs off of like a monorail or something, but it's driven by a chain separate from the monorail. So fairly sophisticated conveyors. Simio can do all of those, and it's actually a fairly simple set of options. The main option is it accumulating or non-accumulating? You know, think about when you go to a grocery store and you put your eggs up front at the beginning, and then your 5-pound bag of flour after it. What happens to that bag of flour, or more importantly, what happens to your eggs, depends on the type of conveyor and the attentiveness, perhaps, of the checkout clerk. But if on a non-accumulating conveyor, whenever anything stops, your eggs, for example, stop at the end, then everything on the conveyor stops. In an accumulating conveyor, whenever anything stops at the end, everything else moves forward until it touches it, or in the case of your eggs, and an inattentive clerk, your eggs get crushed. But there are other options as well, but that's the main option that allows you to do all of those. So normally I would draw or I would build a model for you. I won't just because we're running low on time, but you get an idea of Simio conveyors. While they're far from perfect, they do model a lot of situations that many other discrete event simulation packages find difficult or impossible to do, like processing while it's on the conveyor, merging multiple conveyors together correctly, dealing with multiple speeds. This is a speed of 3 and a speed of 4, merging onto a slower conveyor. All of those things are somewhat difficult to do that Simio does pretty easily. The last topic that I wanted to cover in all of the next minute is vehicles and workers. And luckily, I already did cover workers a bit. So I showed you, the basics of how to use a worker. I didn't go through many of the properties. I would normally go through this example, but I think I'll cut this short for now. But it works very similar to the way I showed you in the server example where I had workers. So workers and vehicles are actually fairly similar, almost identical, except in user interface and a few properties. So this can give you an idea. So let's look at the worker that we looked at before. The worker, it has a capacity, it has a ranking rule, it has dynamic selection of what work it wants to select first. Our worker, the main thing about the workers is we tend to think of workers as somebody who does work, but can a worker carry things? Sure. So a worker can do transport, but the doing work part is the first part of this, and says, well, how do I get from place to place when I'm doing work? And under what conditions, what do I do when I'm busy? Where do I appear? Where do I go when I go idle? Where do I go? Or what is my action when I go off shift, things like that. But then it also has transport logic. So if I want to use a worker to move things around, then I can also do things like, well, how long does it take to load? How long does it take to unload? What is my animation look like when I'm loading and unloading? How long will I wait for a load to appear? Things like that, as well as many of the other things we talked about, the add-on process triggers, financials, etc. Vehicle has pretty much all the same properties and a couple more. The big thing about vehicle is we tend to think of a vehicle as something that does work. I'm sorry, something that transports things around. But a vehicle can also do work. Think of a forklift that needs to lift up a heavy part while it's being processed. So, vehicles can do work, workers can transport, so they are almost identical, except for a couple other things, like vehicle has a reliability, a capability as a device might have, and we all know workers are 100% reliable, so we don't have to have that reliability for workers, right? Okay, so I got through in almost on time, so I'll stop there, and we're, I guess, officially on our 10-minute break, but I'll take any questions during this break.
Folks, if you have any questions, please either type them away in the chat box, or you could unmute yourself and then ask Dave the questions you have.
Okay, I apologize for going through that fairly quickly, but hopefully you got the gist of what we were talking about.
Thank you, Dave, for that. I'm sure we all have kind of a basic understanding of how workers and vehicles are used, and then resources and all the other, and especially interested on how probably to explore how conveyors can be used in terms of modeling and then simulating the accumulated and non-accumulated aspect of it. Thank you for that brief and crisp introduction to those objects. They very much appreciate it. So I guess if we have no other questions, we'll resume our session at 2:10, probably 7 minutes.
Okay, sounds good.
Thank you.